Welcome to the second lecture on LTI models, on state space form, where LTI stood for linear time invariant systems. And what we saw last time is that we could model at least two systems like x dot is ax plus bu and y is cx. Well, it turns out that this is a very, very general description of a large class of systems. And x here is the state of the system. What that means is that x describes what the system is currently doing. U is the input, which tells us how we affect the system, and Y is the output, which measures the aspects of the system that we care about or that we have access to somehow. And the way we should think about these A, B, and C matrices are really that here, AX, well, that's the physics of the system. So A is given to us by Newton, by the laws of physics or electromechanics or whatever it is that we're using to model our system. And there's very little we can do about that. B, on the other hand, that tells us how the input affects the state, meaning this tells us what actuators we have. So if we buy new actuators, we get a bigger B. In other words, B is to a certain degree up to us, the designers who are actually building the systems. Similarly, C actually encodes what sensors we have, meaning how can we actually get information about what's going on inside the system. So A is given, typically. B and C we design when we design the system. And as we will see later on, sometimes we may not have enough control authority, for instance, to make the system do what we want, meaning our B matrix is too measly, which means that we have to buy a better B matrix, maybe buy a new actuator or so. But at the end of the day, a system like this, it's influenced by our control signal, U, that's the input, and out comes Y, which is ultimately the thing we can see. We can typically not see X, but we can see Y, because that's what our sensors are measuring. And the question that all of control theory is really about is how do we pick this input to make the system do what it should be doing? And more importantly, since we only can measure Y, how do we pick U given Y? Unfortunately, we cannot answer that question right away. What we do need to do first is understand these systems a little bit and come up with tools for describing their behaviors, because until we understand their behaviors, we can't pick U's that make the behaviors be what we want them to be. So we're going to do that. But first, we actually need to understand a little bit more about where these systems come from. So let's start with our old friend, the car model. This was the model we used when we built the cruise controller for a car. So what's going on here is that the acceleration of the car, v dot, was c over m times u minus gamma v. So let's put this model on state space form. Well, let's say, first of all, that we're building a cruise controller. All we care about is the velocity. In this case, let's say that the state is actually the velocity. The thing we're measuring is the velocity, which means that y is cx, where c is simply 1. Right? We're simply measuring 1. Well, v dot is given by this expression, which means that x dot, where x is the same as v, is ax, and a here is simply minus gamma, plus bu, where b then becomes c over m. So in this case, we have a one-dimensional, simple system for describing what's going on. Now, let's pretend that instead of building a cruise controller, we're building a self-driving car. Well, clearly, we not only care about how fast it's going, we care about where it is. So in this case, let's make our state the position and the velocity, so PV. In this case, we're measuring the position, say, which means we're taking out the first component of the state, so c is 1, 0. Similarly, this equation still holds, so what we're controlling is the acceleration through the cm, and what remains is my A matrix, where the 1 here simply says that the time derivative of position is velocity, and then this gamma is the same gamma as we got before. So the important point to note here is that the model we end up with, to a certain degree, depends on what we care about and what are the things that we can measure. Now, let's take another model. Here is a pendulum, and the pendulum is attached up here on the ceiling somewhere, and it's swinging with an angle theta. It has length L, and the acceleration of this angular acceleration, turns out to be minus gravity over the length times sine of this angle plus cu. And the way we should interpret this is that what we're doing is we're actually applying a torque up here that allows us to swing the pendulum in certain ways. Okay, let's write this as an LTI system. ouch, sine theta is not linear, so we actually cannot write this as an LTI system. But here is something we can observe. For small thetas, then sine theta is actually roughly equal to theta. So what we can do for small angles is actually replace this thing by theta. So let's do that. For small angles, then, what we get is, well, if we measure the angle, then y is simply 1, 0, where we're taking out the angle and not the angular velocity, because the state in this case is theta, theta dot. Well, similarly, we're having a C here, so the C shows up there in the B matrix, and the A matrix looks like this. 0, 1 here, which means that the time derivative of the angle is the angular velocity, and this G over L term here is the same as the G over L term up there. So this would be the A, B, and C matrices for this pendulum. And again, I want to encourage you to go through the math and perform these matrix multiplications so that you indeed trust that this is correct. Okay, let's do another example. 2 simple robots. Let's say that we have 2 robots on a line, and what we can do is we can control the velocities of these robots. So x1 is the position of robot 1, x2 is the position of robot 2, and we want to somehow control them. Well, first of all, what we get is that x dot is 1, 0, 0, 1, u. We have no A matrix in this case. A is equal to 0, and the B matrix is simply the identity matrix. Let's say that we can measure where the robots are too, so in that case, y would simply be the identity matrix times x, or just x itself, right? So this would be our model of this. Now, let's solve a problem here. Let's solve what's called the rendezvous problem. The rendezvous problem is the problem of having the robots meet. And you know what? Why don't we actually have them drive towards each other? So here's an idea that one can have, where we say that u1 is x2 minus x1, which is simply code for saying that x1 is going to move towards x2. And similarly, u2, let's make that x1 minus x2, then that means that robot 2 is aiming towards robot 1. Well, what we've actually done now is we've designed a closed-loop feedback law where we have written the control inputs in terms of the states in this case, but since the outputs are the same as the states, we're actually writing them in terms of the outputs. Well, if I do that, I get a new system. X dot is negative 1, 1, 1, negative 1, x. And what this corresponds to is instead of writing u here, I'm plugging in these things there, and then you end up with a new system dynamics. That's what's called the closed loop system dynamics. And in fact, if I run this, and let's run it for not 2 robots, but a gazillion robots here, then, as you will see, running exactly this simple controller makes the robots actually meet on the same point. So that was kind of cool. Let's do another example now. This is the unicycle robot we looked at when we modeled the differential drive robot. Again, sines and cosines are unpleasant. This is not linear, right? But cosine for small angles is equal to 1. So let's assume we're dealing with small angles. And sine for small angles is equal to the angle itself. So using that, we get this. But look at this. This is still not linear, because here we have a multiplication. So even when we made this simplification, which, by the way, is a completely stupid simplification, because the pendulum may swing at small angles, but why does the car have to drive in only a direction where we're having small angles? That doesn't make any sense. But the point here is that this kind of simplification didn't do anything. Still not linear. So we need to be a little bit more systematic when we generate linear time invariant models from these kinds of nonlinear systems, because just saying that, let the angle be small and hope for the best won't actually give us all that much. And in the next lecture, we will be systematic in our generation of